Good morning, good afternoon, or good evening. Regardless of when you're checking us out, I am very excited that you are here for another amazing installment of the Richard Watkins podcast. I am your humble host, Dr. Richard Watkins, and the Richard Watkins podcast is a proud production of the Science Policy Action Network, North Carolina's leading scientific research consulting engagement firm. Find out more at sciencepolicyactionnetwork.com. That's span-inc.org. That is span-inc.org. Now, with that out of the way, let's get the proceedings proceeding because we have an amazing episode in store for you today. We have none other than Adrienne Erickcek with us today. Adrienne is an American theoretical cosmologist whose research aims at understanding cosmic inflation, dark matter, dark energy, chameleon particles, and alternatives to general relativity, such as FR gravity. I'm not sure what that is, but we're going to hear a little bit about that. She is an associate professor in the Department of Physics and Astronomy at the University of North Carolina at Chapel Hill. Go Tar Heels. Adrienne, I know I butchered that intro. What did I mess up on?
So there's a wide variety of work there. Some of it dates back to like graduate school, so some of it's, a little out of date. For the past several years, it's mainly been focused, my research has mainly been focused on dark matter and how we can use it to probe the expansion history of the early universe.
Okay, okay. You teed us up here. You teed us up here. Where did you go to school? Take us all the way back. How does someone become a cosmologist? Where did you do undergrad? Where did you do grad school? Did you do a postdoc? Walk us through it.
So I developed an interest in space from a very, very young age. I was really into science fiction starting from like kindergarten. And I wanted to invent the warp engine. I was a big, Star Trek fan, and this like space shuttle going up and down to orbit, that wasn't gonna cut it. I wanted something better. And starting by age first grade or so, I was saying when I grow up, I'm going to invent the warp engine. Um, my father was a kind of lay physicist, had read some popular science books, taken a few physics classes, and he started telling me, you're going to run into problems with this because as you go faster, time slows down. And I thought this was the craziest thing I'd ever heard. So I started really just kind of getting interested in physics and took my first physics class at the Kalamazoo Area Math and Science Center in Kalamazoo, Michigan, and just loved it. I was a little bit worried. I was really into space and astrophysics, and I was a little bit worried that inclined planes were going to not interest me. But I actually just really love math and I love physics. I went to college, I went to Princeton, and I went to Princeton kind of thinking I wanted to study black holes. By that point, I was really into black holes and wormholes, maybe as a more realistic way to get a warp drive. Um, but at Princeton, I caught the cosmology bug, which was an easy bug to catch at Princeton because this was, and I'm going to date myself here, this was the early 2000s, and Princeton was the ground zero for the WMAP revolution, our first space-based high resolution map of the cosmic microwave background. And so cosmology was very much front and center. There was a lot of exciting stuff going on. And I got interested in cosmology. I did a couple projects in undergrad and on dark matter and inflation and gravitational waves from inflation and then went to Caltech for my PhD. Still very much in cosmology and worked with Mark Kamiankowski there and worked on a variety of topics, some of which you listed. And yeah, been doing cosmology ever since.
So I wanted to talk about something really quick, and there was a lot of amazing pieces that you mentioned in there, but one of the things that I would like for you to kind of describe or define is the cosmic microwave background. I know it's important for a lot of what we understand about the universe, but could you break that down for us?
Right. So the first thing you have to know about the early universe is it was very, very hot. A lot of people have an incorrect conception of the Big Bang as like this little speck of light in a sea of nothingness and then suddenly filling the nothingness. It was the exact opposite of that. The early universe was extremely hot and dense. There was no nothingness that we are expanding into. In fact, the expansion of the universe is more the creation of space. It's not expanding into empty space, it's creating new space. And so the early universe was a very, very, very hot and dense place all throughout. And for the first 380,000 years after the Big Bang, the universe was so hot that atoms couldn't exist. The radiation in the universe was so hot that if an electron and a proton tried to get together to form an atom, a hot photon would immediately come up and rip that apart. By about 380,000 years after the Big Bang, the universe had cooled now to 3,000 degrees Kelvin. And this is the temperature where it now became possible for atomic hydrogen to form and it survive. This is a very important moment in the universe's history because it is the moment when the universe went from being an ionized plasma of ionized particles to being atomic gas. The difference there is you can see through hydrogen. It's transparent. So this is when the universe became transparent for the very first time. Now, I mentioned there was this sea of radiation present. So all those photons up until that point had been bouncing around off all the free electrons. But when all the free electrons fell and bound up into atoms, suddenly those photons were free to just go. And they just started going on straight lines. And so when we take our telescopes and we look at very cold photons, the microwaves, we see this glow coming from all directions. And these are literally the photons that have been going on straight lines since 380,000 years after the Big Bang. So for the past 13.8 billion years, they've just been going straight towards us. And we can collect them. And what they give us is a picture of the universe at that time. They carry information about the last thing they interacted with. And the last thing they interacted with was the sea of electrons just before hydrogen formed. And so when we look at this, we see a bunch of hot spots and cold spots. And these hot spots and cold spots have very specific statistical properties. And by studying the properties of these hot spots and cold spots, we can get a very complete picture of what the universe looked like at the beginning. And that tells us a tremendous amount of information. What it tells us is that at this early stage, there were tiny, like 1 in 10,000 density fluctuations throughout the universe at all different scales. And that's incredibly important. That seeded the formation of all subsequent structure. That was the beginning. And the properties of those initial conditions tell us about what happened before that. The way those initial conditions have evolved tell us what the universe is made out of. The cosmic microwave background is really what turned cosmology into a precision science.
Does the cosmic microwave background tell us where the Big Bang occurred? Like, if I were to look in a direction, can I point myself? That's where we started. Does it give you that much information?
Well, so the Big Bang is not a location, it's a time. So I mentioned how the picture that a lot of people have about the Big Bang, and it's, I see it in a lot of documentaries, and every time I see it, I'm just like, no. Like I said, little speck of light exploding into vast nothingness. That is completely the wrong picture. So the better way to think about the expansion of the universe and the Big Bang is imagine putting down a grid everywhere on the universe. So right now there is, a set number of grid lines between you and me, and there's a set number of grid lines between us and Andromeda, our nearest big galaxy. The expansion of the universe is taking all those grid lines, every single one, and moving them further apart. So when we say the universe is expanding, what we're talking about is the distance between any 2 points is growing. I said it was the creation of space. It's new space being created between all objects. So you take that movie backwards. Again, imagine your infinite grid, endlessly in all directions, and all the grid lines are just getting closer and closer and closer together. The Big Bang, what we call the Big Bang, is that mathematical moment when all the grid lines have zero separation. And so the universe is still infinite. There's still an infinite number of grid lines, but they have zero separation. So the Big Bang didn't happen at any one place. The Big Bang literally happened everywhere because the Big Bang was that moment when all points in the universe were at zero separation. And there was no emptiness that it was expanding into. So the Big Bang doesn't have a spot. The Big Bang has a time, but it happened everywhere.
All right, so I've got a bunch of questions, and they all stem from my ignorance and my fascination with all of this. Um, so you said it's not expanding into nothing. And I get that, coming from you, but then I start grappling with what even is the concept of nothing. Is nothing an actual thing?
I
You're,
mean,
you're
we have
laughing at me. Is that a silly question? Have your students
no,
asked you
no. I mean,
that?
when I say nothing, I mean empty space.
Yeah.
So space, and that's a good question about, okay, so what is empty space? And is empty space really empty? We'll get there. Um, that's a very good question. But what I will say is there is a physicist's definition of the vacuum, i.e., empty space. And when I say nothing, I mean empty space. And what I'm saying is that we are not expanding into empty space that already existed. It's that new space is being created all the time. And so we're all getting further apart from everything else. Um, but we are, it's not because we're like an explosion flying into a void. It's that we started out everything really, really close together, and now everything is just moving apart. Now, this is an important point where I want to add a caveat here. Some things are not expanding. The solar system is not expanding. The Milky Way is not expanding. Even our little local group of galaxies is not expanding. Andromeda is actually falling towards us. We're gonna collide with Andromeda in a few billion years. Um, but anything that's not gravitationally bound right now is moving away. So our little local group of galaxies and everything in it is gravitationally bound, and we're a little nugget held together by gravity. Everything outside that is new spaces being created in between, and it is flying away from us.
Another one is you're saying, it's not where did the Big Bang occur. The question is, when did the Big Bang occur? And that's also another concept that really just tickles my brain because, and obviously, correct me if I'm wrong. So, space was created during the Big Bang and it just keeps being created. But isn't time also being created?
Yes. I mean, time is a so in the it depends on how you describe time is one thing. I would say the easiest way to think of it is that time there is the expansion of the universe sets a rest frame. There's a frame which is at rest with respect to the expansion of the universe, and a clock in that frame just ticks. And so, there is a time direction in that frame, and that clock, if there is a clock that's just at rest in the expanding universe, that clock ticks. And all I can say with confidence is something really interesting happened to that clock 13.8 billion years ago.
All right.
That clock saw something.
Yes. Very, very good. All right. Let's get into some, and we'll come back. And I know there were some things that you wanted to talk about. And another thing that I realized before I go on to something else is a thought that I have is it sometimes seems as though, our vocabulary and our ability to communicate with one another is limited, but we're describing things that are infinite in nature and they kind of define what we conceive as like reality. So when you're saying, "Oh, the universe is expanding," and the obvious question that is in somebody's mind is expanding into what? And then you're like, "Oh, it's expanding into nothing." And then you might say, "Well, a great way to understand this is like bread baking, right? And you've got like dots on the bread that represents whatever. And as it grows, the things move further and further apart. So it's not that it's expanding into something. What happens is that messes up somebody's brain because they're thinking of, wait, no, it's expanding and taking up space in the oven. So it's that's even hard. So we have a hard time describing of what's happening.
Yeah, I mean, the baking bread analogy is a good one. I've definitely used it. The problem with it is exactly what you said. We're used to bread having edges. So I need you to imagine an infinite dough. Dough infinite in all directions, but there are raisins in the dough. But it's infinite dough. There's no edge to the dough. It's just a bunch of raisins in an infinite volume of dough. And then as the dough expands, the raisins get further and further apart. That is a good analogy. You just have to, like I said, you have to abandon the notion of the oven. You have to abandon the notion of the crust of the bread. There is no boundary to the bread. It
Yeah.
is just a an an endless sea of dough in all directions.
Yeah. We have to have, I feel like we have limitations as humans, like our ability to imagine, our cognitive capacity. And I feel that discussions of cosmology really brings us to the brink of what we're capable of as far as thought. Because one of the things we're talking about, and I know, you're big into math. Is this concept of infinity. That's a difficult one because I know in mathematics it is an accepted principle where if you take all of the even numbers that exist, it's an infinite number of even numbers, which is also equal to the totality of all numbers. And you're like, wait, how is that possible? Shouldn't it be half of all numbers? But it's not like that. It's
Right.
there's different quantities of infinity that are also equal. Come, this is too much for the brain to deal with.
Yeah, no, I mean and I should say, we're not 100% sure that the universe is infinite volume. It could kind of loop back on itself. We could be living on the three-dimensional analog of like a spherical surface that has so like a sphere has a finite area. Like you keep going and you eventually loop back. We could be living in a three-dimensional version of that. We see no evidence of that. At the moment, all of our, the cosmic microwave background is one of our best probes of this. We see no evidence that we are not just in a nice, you know, Euclidean geometry, like a flat piece of paper that goes on forever. We see no evidence that the universe is like turning in around on itself. But just like it's really hard to perceive the curvature of the Earth while you're sitting on the surface, it is possible that the universe is more spherical and we just haven't seen it yet because we just only see a very small bit of the universe. Um, so we have limits on this. We can put limits on if the universe is curved like a ball, how big is the radius of the ball? And the answer is very, 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 very big because as far as we can see, it looks flat to us.
That's true. I think we're approaching a good segue. So we're here with Dr. Erickcek of the University of North Carolina at Chapel Hill. Are we talking about cosmic inflation here?
No, cosmic inflation is something even a little stranger.
Ooh, I love it. The stranger, the better. So what is it?
So, so okay, we talked about the expansion of the universe, and the expansion is this, creation of new space. Gravity should be trying to pull everything back together. You can understand that gravity would be fighting this. Everything's moving apart, but gravity is trying to pull everything back together. So you can think the default state of an expanding universe that contains matter, like us, should be that expansion is slowing down. That leads to some two big problems. One, we look at the expansion today, it's actually speeding up. The universe's expansion is accelerating right now. This is dark energy. This is weird. This was not expected. Gravity should be slowing everything down. And no, no, no. We are expanding at an accelerating rate. It actually turns out that it really solves a lot of the problems of early universe cosmology in terms of setting up the cosmic microwave background the way it looks. And the cosmic microwave background, like I said, has some really interesting properties. And getting, it set up like that is a lot easier if you also postulate that the universe went through an accelerated period of expansion very early on. And that is what we call cosmic inflation. So you can think of inflation as this moment either right with the Big Bang or right after the Big Bang, where the universe basically had a growth spurt and had a brief instant of extremely accelerated expansion. And what this does for us, you're going to like this, is this moment of extremely accelerated expansion basically takes little quantum fluctuations. Quantum mechanics tells us that nothing ever sits still, everything's always churning and bubbling under the surface. That little growth spurt takes those quantum fluctuations and spreads them across the universe. And that gives us the initial conditions we need for the cosmic microwave background. And that's why we're here. That's why some of places of the universe are a little denser or a little less dense. It's all quantum fluctuations. And it was all during inflation that those quantum fluctuations got stretched out to cosmic scales. And so
Goes
that's what
back.
cosmic inflation is. It's the universe's growth spurt in the first fraction of a second.
I love it. So I have to slow you down again because you're dropping little nuggets, and I actually want to stop you and have you define everything, but I can only do it on a certain set of things. So we had on a previous episode a computer scientist out of University of Chicago, and she was talking about quantum computing. So for folks listening at home, this is now their second time that they've heard the term quantum. You're using it in a bit different way. If I understand correctly, is this kind of relationship with like particles and waves, but break it down, what is quantum, and explain it in how you're using it when describing cosmic inflation.
So I would say the piece of quantum mechanics, and quantum mechanics is a huge branch of physics with many different applications and facets. But the piece of it that I am using here is quantum mechanics comes with an idea of uncertainty. And it means that nothing can ever be precisely located. If you know where it is, you don't know exactly how it's moving. And if you know how it's moving, you don't know exactly where it is. Okay, so why is that important to me? It means that in the initial universe, it's impossible to say that the density of the universe was the same everywhere. Because to have the density of the universe be the same everywhere would require knowing where all the particles are. And quantum mechanics says you can never know where all the particles are. So just randomly, no matter how you try to set it up, there's going to be a little bit more particles over here and a little less over there. And that's going to be kind of churning and fluctuating all the time. And so the idea is, and then it gets really weird, is quantum mechanics tells us that particles can even just pop in and out of existence. So you can start with what you think is empty space. And we said, empty is a complicated concept because quantum mechanics tells us that there is no such thing as empty. Particles can constantly be popping in and popping out of existence. And so in terms of the cosmic inflation, the idea is that there is always this kind of quantum foam. If you zoom in enough, you'll see this kind of churning particles popping in, popping out, popping in, popping out. And normally we don't perceive that unless you do some very high precision experiments. But in the early universe, this was happening. And because of inflation, it took that quantum foam that's usually too small to see, too small to perceive, and stretched it, and it basically imprinted on the cosmos. And so when we look at the universe and we see galaxy, 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 empty spot, galaxy, what we are really seeing is that kind of imprint of the quantum foam that's just stretched across the sky. And we know this, to mention the math, the statistical properties of these, overdense, underdense regions that we see match the statistical properties of the quantum fluctuations that would have resulted from this.
That's absolutely fascinating. the fact that there's just so much uncertainty is, I don't know, intellectually liberating for me, right? I find it absolutely fascinating that that is like that. So again, you're very great with segue because almost everything you say leads into the very next thing I'm going to ask about, and that is dark matter, dark energy, right? You mentioned dark matter. So let's first start with dark matter. What do we know about dark matter? And why is it important as far as our understanding of the universe?
Absolutely. So dark matter was first discovered in some form back in the 1930s by an astronomer named Fred Zwicky. And what he did was he measured the motions of galaxies inside a galaxy cluster, a group of galaxies. And based on the light he could see, he could estimate how many stars were in those galaxies. And what he found is those galaxies were moving way too fast. Given the amount of mass in the stars that he could see, those galaxies should be flying away from each other, and yet they were bound and circulating. And he said there must be some dark material. That's what he called it. Now, this was kind of forgotten. This was the 1930s, and physics got distracted in the late 30s, early 40s. And even by the time the war was over, everybody was really excited about nuclear physics still. And so, even astronomers kind of turned their attention to figuring out how stars work, because now we could finally figure out how stars work. And nobody really remembered that this weird finding until Vera Rubin and collaborators in the 1970s looked at how galaxies were rotating and saw the same thing, that the galaxies were rotating way too fast, and there had to be a lot of dark material that was not accounted for in the stars in order to keep the galaxy from just flying apart. And so by 1970s, 1980s, we knew there was a bunch of matter. It has gravitational properties of matter. It gravitates like matter, but we can't see it. And it wasn't really known yet, okay, is it just like rocks? Is it a bunch of dust? Is it just dark? Then we realized that I mentioned the early universe is extremely hot, really, really hot. A couple minutes after the Big Bang, it was hotter than the inside of the sun. And so a couple minutes after the Big Bang, the whole universe is a lot hotter than the inside of the sun. Now, what's going on inside the sun? Why does the sun shine? The sun shines because it is fusing hydrogen into helium. It is taking two hydrogen nuclei and putting them together to make helium. That is why the sun shines. This happened throughout the entire universe in the first couple minutes. And we actually see and measure the helium that was produced as a result. And those measurements of helium tell us very precisely how much normal matter, protons, neutrons, the stuff that makes up you, me, the periodic table, all of chemistry, we get a measurement from the amount of helium that was produced during this process of how much atomic matter there was in the early universe. And it makes up about 5% of the energy density of the universe today. So only 5% of the energy density in the entire universe right now can be found on the periodic table. The cosmic microwave background confirms this as well. Well, what's the rest of it? Well, about 25% of the rest of it is matter. It's gravitationally there. We see it in galaxies, we see it in galaxy clusters. It gravitates. But now we know it's not just that it's dark, it's made of something completely other. It's not made of the same stuff we're made of. It's not made of protons. It's not made of neutrons. It's not dust. It's not rocks. Even in the very, very, very early universe, it was something else. And so what do we know? We know that it is stable. We don't see any evidence that it's decaying anywhere in the universe. We're looking, but we don't see any evidence yet. So it's very long-lived. It's stable. It's electrically neutral. It can't talk to radiation. If it had charge, we'd see it radiating. It does not have charge. And it was relatively cold through most of the universe's history. No known particle checks all those boxes. There is no known particle that checks those three requirements. And so
Hey,
we don't
Dr.
know what it
Erickcek,
is.
can I jump in really quick?
Yeah, of course.
How does the idea of dark matter relate to all of the conclusions that we come to from the cosmic microwave background? Like, are they, go ahead.
It's there. We have to have it. We cannot explain the cosmic microwave background without it.
So, a follow-up question is when we say that the universe is being created as it expands, does that also take into account dark matter? When we're saying that, are we also implying that dark matter is created, or are we not implying that? We actually don't know.
So dark matter was created at some point in the early universe. When I say new space is created, I'm saying that's empty space. So the dark matter, the kind of number of dark matter particles in the universe, we think was established fairly early on. We don't know exactly when. Um, but it has been basically steady since then. So the dark matter density is falling as the universe expands. So the dark matter is just getting stretched out. It's, the space between the dark matter particles is growing, except in gravitationally bound regions like galaxies, where, you know, our local group of galaxies is sitting in a vast cloud of dark matter
Wait, so
that's all gravitationally bound.
gravity has an impact or influence on dark matter.
That's one thing we know about dark matter is it is matter. It gravitates like matter.
Understood.
It's attractive. It clumps together like matter. That's why we call it dark matter. That's
Understood.
the one thing we know about it is it gravitates, and it
Okay.
gravitates exactly like cold matter.
Okay. So our next question, and that was a new one, cold matter. So the two categories that are in people's mind is dark matter and cold matter. Cold matter represents everything that we know of, the things that you and I are made out of, the elements on the periodic table. Is that what you're referring to when you say
No,
cold matter?
when I say cold matter, I mean stuff that's moving much slower than the speed of light. So I'm
Okay.
distinguishing it from photons. Um,
Understood.
I'm distinguishing it from light particles that are really, really hot. I'm
Okay.
saying that
Okay.
anything that is, you know, not moving at the speed of light, not relativistic, cold.
Okay.
So that's us, and it's dark matter.
Understood. Understood. All right. Sorry to cut you off. Hopefully, I didn't derail what you were saying
No,
there. I apologize.
no, no, no. So this is important. So yeah, we know that dark matter is there. We see it in many, many ways, including the microwave background. That there is no way to explain the hot spots and cold spots in the microwave background without dark matter. Those properties clearly say that, yeah, the electrons were all tied up with the photons and bouncing around, but there was something else that was gravitationally just clumping, oblivious to the hot radiation around. It was just gravitationally clumping. And that's important because we wouldn't be here without it. Galaxies would not have formed by now without this like head start to structure formation and ability to gravitationally collapse. So no, we absolutely need dark matter. We see it everywhere we look for it. We just don't know what it is.
And we're going to go to dark energy here, but I do have another question because you said there was a period of your life where you were enamored with black holes. Um, what's the relationship with dark matter and black holes? I mean, do black holes just collapse dark matter onto the singularity? What's going on there?
That's an excellent question. Okay, so let's unpack first of what is a black hole. So a black hole is a region where gravity has gone amok, right? A black hole is literally a region where so much mass has has been collected in so small a volume, the density got so high that basically gravity just won over everything. And we think, why am I not sinking to the center of the earth right now? It's because, the ground is stopping me. Ground is stronger than gravity. Gravity wants me to sink to the center of the earth, but the ground is holding me up. Gravity gets so powerful that nothing can hold it up. Not atoms, not anything. It just takes it all the way down to, volume zero. That's a black hole. Black holes exist. We detect them in many different ways. All the black holes we have detected thus far are consistent with being dead stars or being the combinations of dead stars. When a star dies, when it runs out of fuel, a big star, not our sun won't do this, but a big star, when a big star dies, it runs out of fuel. It can no longer keep doing its nuclear reaction. It shuts down and gravity wins, and gravity collapses it down to nothing. And that is a black hole. And the black holes we observe are consistent with that origin. We see black holes of all sizes, and the big ones, the really, really big ones, like there's a million solar mass black hole at the center of the Milky Way. We think that probably grew by a bunch of dead stars, followed by eating a bunch of gas. Key point here: the black holes we know about, they all form from normal matter. They are the remnants of dead stars. The black holes then eat gas. They are things that formed in the relatively late universe by eating normal matter. And I just told you dark matter has a different budget. Dark matter is not made of normal matter, was never made of normal matter. So the black holes that we know about are not dark matter because they formed from normal matter. And dark matter can't form from normal matter. Dark matter is something entirely else. So those are called astrophysical black holes. They're the black holes we know about, the black holes we see. The hypothetical idea is maybe there's another type of black hole, a primordial black hole, a black hole that was created at the beginning of the universe somehow. Those could be dark matter. A primordial black hole that was created at or shortly after the Big Bang, not from normal matter, but just from something else, then those could still be around and those could be dark matter. They check all the boxes. They're stable, they're electrically neutral, they would be non-relativistic. They could be dark matter. So that is a candidate for dark matter is primordial black holes, but we don't know if those actually exist. And we're not sure how to make them.
Oh my gosh. Gosh. Anytime I hear the word primordial, I'm just like, my goodness. Again, Dr. Erickcek right here, University of North Carolina at Chapel Hill. A huge shout out to Fusion. I had an opportunity to meet Kim Boudil at the Lawrence Livermore National Laboratory. She was actually hanging out in Phillips' laboratory not too long ago. And that was just absolutely amazing. Let's shift on to dark energy here. We've talked about dark matter. Wait, oh, gosh. Before we go to dark energy, please forgive me. I gotta ask one more question about black holes. Can a black hole get so large that it stops being a black hole? What, like, is there any theory behind a black hole just never stops being a black hole? It will never reach like an equilibrium where it's like, I'm through eating things. I'm full now. I'm gonna give stuff back.
Not quite. So black holes, there is no size limit to a black hole.
Yeah.
Now, important to know, misconceptions about black holes. Black holes gravitate, but no more than anything else of their mass. So I said the sun is not going to turn into a black hole. It's not going to turn into a black hole. But imagine if the sun turned into a black hole. It would go dark, but it would not immediately suck the Earth in. The Earth would continue to orbit just as a solar mass black hole gravitates the exact same way as a solar mass star. So the Earth would continue to orbit. It'd get very cold, but it would continue to orbit. It's not like the black hole. Black holes don't suck like vacuum cleaners. They gravitate exactly as strongly, no more, no less, as anything else with the same mass. So
You know
black
what?
hole,
Thank you. Black holes are out there getting a bad rap. People are just thinking that it's just gonna eat the whole universe, but they're just cold, right? They're
they're
just
just
like
they're just
anything
dark
else.
and they just have mass and they gravitate like anything else of that mass. And so we see stars that are orbiting black holes, and we see the stars in the center of the Milky Way orbiting a black hole. Sometimes black holes get fed, and then things get exciting. If you throw a bunch of gas into a black hole, it eats it up, and before it eats it up, it gets it moving really fast. It's really bright. We see these objects called quasars. They're actually the brightest objects in the night sky. We can see them really, really, really far away. Um, And when you feed a black hole, it puts on a show for you. The black hole at the center of our galaxy is quiet right now. It there's not much gas left in the center of our galaxy for it to eat, so it's just kind of sitting there. But it's not going to like consume the entire galaxy. It's just sitting there. It only will grow if you feed it, if you throw stuff into it. It can't like collect stuff itself any more than anything else with that mass.
Like, so right at the boundary of like the event horizon, if you have a quiet black hole, is that space right outside of it, is that considered empty?
Fairly about as empty as it can be, yeah.
Okay.
I mean,
There we go.
inside a galaxy, there's always the intergalactic medium, and nothing's ever really, really empty. But yeah, I mean, if you were to take a spaceship to the edge of the black hole at the center of the Milky Way, yeah, you would cross the event horizon not really knowing much was up until you tried to turn around, and then you'd realize that you're doomed.
Just
So,
when I thought it
be
was
careful.
safe to
Like, don't
befriend,
cross, but you'll
just
just
when,
you'll just you won't really see anything special. You're just kind of like, oh, and then you're like, okay, I'm ready to turn around now. Oops, sorry, no, you're not. You're not going anywhere.
ever,
But you're on
ever
a one-way
again.
trip to the center.
Well, it's a turn to spaghetti, I think.
Well, so
Um,
that depends on the size of the black hole. So small black holes, like solar mass black holes, yeah, you'll be ripped apart and turned to spaghetti before you even get to the horizon. Big black holes, like the one at the center of the Milky Way, nah, you'll get across the horizon just fine. You won't feel a thing till you get later.
this is one of these conversations where I feel like I'll know less after we talk. I don't know
That's not
why.
what I
I
want to
feel
do.
like um let's get into dark energy. Can you give us a definition of dark energy?
Okay, so I mentioned the energy budget in the universe. So right now, the universe as, what is cosmology if not the understanding of the content of the universe? So here we go. The cosmic pie chart. What is the universe made of? I said 5% normal matter, 5% periodic table stuff. We're talking all the stars, all the planets, all the gas. Everything that chemistry can tell you anything about. That's 5%. Then I said 25% dark matter. So this is some matter, it gravitates. We don't know much else about it except it gravitates, but it's some other type of matter that gravitates. Okay, what's the other 70%? I mentioned that we were very surprised to discover in 1998 that the universe's expansion is accelerating right now. The distant galaxies aren't just moving away from us, they're moving away from us at a faster and faster rate. This is weird. Gravity should be pulling everything back together. Gravity should be fighting the expansion of the universe, not driving it. This was as surprising for cosmologists as throwing a ball up in the air and instead of seeing it slow down and then eventually fall back, seeing it just like fly up into space away from you. This is weird. It seems like we have a component of the universe that is that does not gravitate the way normal matter does. Let's just start there. Okay, how do you do anti-gravity? How do you get things to fly, be pushed apart? Turns out that Einstein's theory of general relativity allows this. There is anti-gravity inside general relativity. It is something that can be mathematically accommodated for in general relativity. You need something that has negative pressure. I don't even know what negative pressure means, except it means that it kind of anti-gravitates. What you really need is you need something that does not dilute as the universe expands. Okay, so we've been talking a lot about the expansion of the universe. It's the creation of new space. And so if I have two dark matter particles, as the universe expands, they get further and further away from each other. The dark matter density goes down. If I have two photons, they get further and further away from each other, and they get redder and redder and redder. Their density goes down as the universe expands. The universe is becoming emptier and emptier and emptier. But what if there's something that doesn't do that? What if there's something whose density stays roughly constant? I expand and I just get more. The density doesn't change as the universe expands. If there is such a substance, it would cause the universe to accelerate. It would cause this accelerated expansion. So this is what we call dark energy. We don't know much about it, except it is causing the universe to accelerate. And in order to do that in the context of general relativity, it's got to be something that as the universe expands, its density does not change. This is why it sometimes goes by the name of vacuum energy. We talked about what is empty space. Oh, empty space is complicated. It seems like dark energy maybe could be the energy associated with empty space itself, i.e., get more space, get more energy. Um, that's well and good. You can even start getting excited that, hey, well, quantum mechanics tells me that empty space isn't empty, and that's dark energy. Yeah, the problem with that is when you actually use quantum mechanics to calculate what should the density be of empty space, you get an answer that is a factor of 10 to the 120th power too big. And this is a well-known problem in quantum mechanics. It just gives nonsense if you try to calculate this. And people were kind of willing to ignore it until cosmology came along and said, actually, we do need a little bit of empty space energy. Not nearly as much as you were saying, just a little bit. And we don't know where any of this comes from. We're baffled.
There, there are or have to be massive consequences of universe expansion and the increased speed of that expansion. Now, I don't know what that is because here on Earth, I don't I'm not really aware of that consequence. What is the consequence of cosmic expansion and then the increased speed of that expansion?
Luckily for us, not too much. So if dark energy were a lot stronger than it is, if there was more of it, if there was as much as quantum mechanics predicts there should be, we would have problems. Galaxies would never have formed. Things would have been ripped apart and expanding too fast for galaxies to ever have formed, much less stars. So we would not be here. And so there's an anthropic argument for why dark energy is as small as it is. That if dark energy were too big, we would not be here. Um, the little bit of dark energy that we have does not affect us much. It means that it's bad news for the cosmologists of the future. It means that in billions of years, we will lose sight of all other galaxies that are not currently bound to us. So we will
Right. So
lose we will lose the image of the cosmos. The other
so our
galaxies,
galaxies had to form when they formed because they could not form in the future. I'm not putting a time. Is that what you're saying also? Okay.
I said that right now the universe is 70% dark energy. So we are, entering dark energy domination. But remember, the matter density, you go back in the early universe, the matter density is going up as you go back. You take all the dark matter particles, you make them closer together. So for a long time, for about 10 billion years, the universe was matter dominated and the expansion was slowing down and galaxies could form. And we had a nice long matter dominated era where, gravity was fully in charge and galaxies were forming and galaxies were merging and structure was forming. And we had a nice long period of that just stopped, about 4 billion years ago, that things started accelerating away. And so it means that all the structure that has ever formed, that will ever form, has formed. And now everything's flying apart. If it's not gravitationally bound now, it never will be. That is what dark energy is doing. But we're good. We're good. We've got our little neighborhood of galaxies. We're gravitationally bound. As long as dark energy doesn't do anything crazy, like getting stronger with time, we're totally fine. But our little local group of galaxies will become increasingly isolated.
That's fascinating. It just really makes you realize just how special now is. You take it for granted. You can't take it for granted after, talking to a cosmologist. If you talk to a cosmologist, if you talk to Dr. Adrienne Erickcek of the University of North Carolina at Chapel Hill, you would really make the most of every moment you have because it is of the uniqueness and how special it is on the level of cosmic importance. That's amazing. It makes my hands sweat a little bit. I don't know why. Um, the
Give or
next
take a
question I
billion
have,
years, I'll say. You talk, your background's in biology. In terms of evolution of life, this is all, much longer time scales. I'm saying, okay, a few billion years from now, this is going to happen. A few billion years ago, that happened. This
but I will tell
cosmologists
you,
talk about, time intervals in billions of years. For the most
but it
part, things
seems
are
like you
happening
all
pretty
have a
slowly.
better grasp of these major concepts than I would say biologists have on, wait, where did life on Earth come from? Like, it feels like you have a much better grasp than I feel that, evolutionary biologists have on, like, wait, how did life come to be on the planet?
It may be only 5% of the universe, but chemistry is complicated.
Yeah, that's true. That's
That
very true.
one thing we know about dark matter and dark energy is they are simple. Dark matter, we don't know much about it, but we know that it doesn't radiate. It doesn't, if it has chemistry, it doesn't burn. It doesn't emit light. It's relatively inert, and that makes it simple. You only have to worry about gravity. Biology is way more complicated.
Well, you mentioned biology, and that's life forms. You have a topic on here that seems to combine zoology and physics. We've got a chameleon particle here. What are chameleon particles?
Okay, so we mentioned dark energy. Dark energy is uncomfortable. Cosmologists have made our peace with it now. It's been 28 years, but nobody wanted this. Okay, this was not something that anybody. The people who discovered dark energy, they were setting out to discover how quickly the universe was decelerating. They were very surprised to see it accelerating. Um, it is tempting to try to think of, okay, maybe we just don't understand general relativity. Maybe instead of invoking some kind of crazy vacuum energy, we just need to change the laws of gravity. This is not easy to do. General relativity might be my favorite theory of physics because it is so elegant and it is so beautiful and it is so resistant to change. So if you say, okay, I want to change gravity so that galaxies accelerate away from each other without having to invoke any crazy dark energy. Okay, great. You try to do that, and you end up changing gravity everywhere, including in the solar system where it's been very measured precisely and agrees perfectly with general relativity. Thank you very much. So this is the challenge of modifying gravity, is how do you modify gravity between galaxies without changing gravity between the sun and the earth? Because we've measured that really, really, really well, and general relativity is right on. This is chameleon gravity. And the chameleon here is evoking the idea that it can blend, that it can hide. And so there was a proposal. Oh, sheesh, when was this? This would have been like 2005, 2006. Justin Corey and Amanda Veltman had this idea of how to modify gravity in a way that would mimic general relativity in local dense environments. And by dense environment here, I mean inside galaxies. The environment inside a galaxy is dense compared to the emptiness between galaxies. And that is what chameleon gravity is. And I studied it quite a bit, earlier in my career, trying to understand, is it successful in evading solar system tests of general relativity? And the answer is yes, in certain constructs. How stable is it in the early universe? Turns out not very stable. It runs into trouble in the early universe because it has this weird kind of, switching property. And that switching property of being like GR, then not like GR, then like GR, then not GR gets a little messy in the early universe. Um, but yes, that is what chameleon gravity is. It's the idea that if you're going to modify general relativity, you have to do it in a way that the modifications are hidden but they camouflage in local environments because general relativity is extremely well tested inside the solar system.
I love it. I love it. Now, you use chameleon. I think the master of camouflage is the cuttlefish, but we will accept chameleon today.
Cuttlefish
Dr.
gravity just doesn't have the same ring to it, does it?
No, it doesn't. Cuttlefish gravity. I don't know. I don't know. People might like it. But I will end like this. It is a privilege and honor to host this podcast. I talk to the most brilliant and influential people across the country. Thank you for your work and taking the time out to talk to us about very amazing concepts. I mean, I'm going to be up all night thinking about this, and it's always really fun because I might go to the barber shop and folks are talking about sports, really big into basketball. And then I'm like, well, what do you think about the chameleon particles? And then like everything gets like really quiet. But I want to end this the same way I end every single episode because I know that I should have asked question A. I know I should have asked question B. And an hour's just not enough time. So I'm actually going to turn it to you, Dr. Erickcek. What question should I have asked? And then if you could answer it.
Oh my goodness. Okay, you actually asked you hit all the major parts. I guess one question that I say is, how are we going to learn more? What should we be looking forward to? I like to, this is an active area of research. We've covered all the things we don't know. We don't know what dark matter is. We don't know how dark energy works. Um, we don't know the details of how cosmic inflation happened. How are we going to learn more? What's on the horizon? What do we have to look forward to? And I'll say that we have a lot to look forward to. It's a great time to be a cosmologist. New data is coming in. So we have some very interesting results that just came out in the last year or two from the Dark Energy Spectroscopic Instrument, DESI, that seems to maybe be giving some hints that dark energy is doing something interesting, that it isn't just constant, that it is evolving in some way. That is extremely exciting. This measurement was done by just mapping the positions very precisely of millions of galaxies. So we need telescopes. We need, that's what we need. We need high precision telescopes to map all the galaxies, and this is underway. The Rubin Observatory had its first light about a year ago. We are hoping that it is going to discover a lot of new dark matter structures, which would tell us about the dark matter particle, how it's distributed, what its limits are. Is it perfectly gravitationally inert, or does it have any sort of random motion? We're really excited about new discoveries there. The Roman Space Telescope is due to launch later this year, and it's promising major breakthroughs in basically every area of cosmology, dark matter, dark energy. So it's a really exciting time. New data is coming, but of course, these are all major experimental efforts. So if you like these questions, we need to support basic fundamental research and telescopes and new efforts to try to understand our universe. None of this comes cheap.
No, I don't imagine that it does. Yeah, absolutely. Dr. Adrienne Erickcek, Department of Physics and Astronomy, University of North Carolina at Chapel Hill. That was an amazing conversation. Again, Dr. Erickcek, thank you so much for being with us today. And she did say a funding request. So make sure that you are funding basic scientific research as it shapes our understanding of the universe. This has been another amazing episode of the Richard Watkins Podcast. Again, the Richard Watkins Podcast is a proud production of the Science Policy Action Network. Check out the Science Policy Action Network at span-inc.org. And remember that the future is not something to wait for, it is something to build. And until next time, take care.